Hello and welcome to section 7.4, which is about using a substitution strategy to solve a linear system. So in the last section, we talked about how you can solve the linear systems by graphing them and finding the intersection point. But it's not always convenient or easy to make two graphs. And so a lot of people actually prefer to solve these systems algebraically. There's two main methods. We're going to learn one of them today. So this one's called substitution. The next lesson will be on the second method, which is called elimination. And both methods are going to be used in future math classes as well. So you want to make sure if you do have any questions about anything, please make sure that you ask, especially as you're working through your assignments. Okay, so let's start by filling out the first part here. So in previous lessons, we learned how to solve the systems by graphing. However, that can be time consuming and it can be difficult to sometimes also find a clear answer. If your two lines that you graph intersect somewhere, but it's not right at a grid point, you can end up trying to estimate answers and you may not be 100% certain of them. So substitution and elimination strategies, or the algebraic ways of doing these questions, allows us to have an exact answer. So luckily, there are two other common algebraic strategies that we can use, and they are called, as I've said a few times here, substitution and elimination. So today we're going to focus on the substitution method. So how it works is a system of linear equations can be transformed into a single equation where you only have one variable that you don't know by substituting an equivalent expression in place of the variable. So I have a fully written out example here that can help us understand how to solve by substitution, and then I will show some examples that we'll work through together. So let's say, for example, we have these two equations, and I have a 1 and a 2 beside them just to call them equation 1 and equation 2 to make them easy to refer to. So our first equation is 3x plus 4y equals -4. And the second equation is x plus 2y equals 2. So our first step is to choose a variable that's easy to isolate. So in this example, if you look at where the x's and y's are, which of these x's or y's is going to be the easiest thing to isolate or get alone by itself? And I think it should be pretty obvious that this x is going to be the easiest one to get alone by itself. The rest of them all have a coefficient in front, which adds another step. In order to get this x by itself, all we would have to move is the 2y over to the other side. So right away, we're trying to choose the easiest way of doing this. So in other words, I want to try and move this positive 2y over to the other side. And the way I'm going to do that is by subtracting 2y from each side. So that is how I end up with this equation here. So I have now isolated that x, and it's now equal to -2y plus 2. So first thing is to choose the variable that you're going to get by itself, and then you're actually going to isolate it. Now what we're going to do is substitute it in. So we know that x is worth or equivalent to -2y plus 2. So what we're going to do is take that -2y plus 2 and put it in the place where we see x in the other equation. So we're literally going to copy this expression in place of x. Now be careful, this was 3 times x. So when we go ahead and substitute, we have to put brackets around this -2y plus 2. So you can now see that that has been substituted in place of the x here. That gives us now a new equation. Now we can go ahead and solve. I'm not even going to go through the solving steps in detail. It's all written out here, but you eventually solve it until you get the other variable equal to a certain number. So the neat thing about this step here, why it's important or useful to us, is that we can now solve this one for y. It's solvable because there's no more x's. We've eliminated, in a sense, all the x's because we substituted them away. So this one is now solvable for y. Okay, so now that we've done that, and I mean, I guess there's a few things you want to remember when you're solving. Of course, we would distribute this 3 to both terms. That's how we end up here. Then we collected some like terms. Then we isolated. Those are steps that we have done in previous classes quite a bit, and you'll see them in the examples coming up. Okay, so looking at step 5, well, now we know y. So this is only half our answer. So we still need to find x. So the way that we're going to do that is we're going to solve for the missing variable by choosing one of our equations and solving it for x. So now we're going to substitute again. So now we're going to take the y that we know about into either of the original equations. And so here it is. So we know, actually here I will just highlight the 5. So we're taking the fact that y is 5 and now putting that into one of our original equations, and that allows us to now solve for x. So here is now the other half of the answer. Now, step 6 is something that people forget to do. They've done all this great work, and then you have to remember you're going to state your solution as an ordered pair, which means it has an x and a y value. Which one goes first and which one goes second? Well, x is always written first. Even though we found y first, we're going to write the x first and then the y second. And so it always goes in that order. And what that means is if we were to graph this point at -8, 5, there's the answer. So if we did go back and graph these, our answer would be there on the Cartesian plane. Now, just like we did in previous sections, you're going to check or verify your answers in both equations. So you're going to check -8, 5 in equation 1, and you're going to check it in equation 2. I'm not going to go through that. It shows it here. You do them both until you end up with the same left-hand side as right-hand side. But that is exactly identical. This step is the same as what we did in the last section. So even when we were graphing, we would check our answers in both equations. So that's not new. Just for length's sake of the video, I'm going to move on to actually show this through some new examples. Okay, so that's an example of a fully written out question with the steps written out. Here we're actually going to apply what we've learned. Okay, so there's 2 questions here. I'm going to focus on question A first. First of all, I want to ask myself which of these 4 variables is the easiest one to get by itself. And I think that this one is the y. Okay, y, it doesn't have a coefficient in front of it. All I have to do is subtract 4x from each side to do that. So I'm going to rewrite my second equation as y equals negative 4x plus 5. So I do still have equation 1 and 2, or you can label them A and B. It doesn't matter. I'm going to call them A and B this time, just for variety's sake. Now what I'm going to do is take this value of y, and I'm going to substitute it in to this y here. So my next line of work will say 2x minus 4, and then in brackets, times negative 4x plus 5. So when you're substituting, use brackets. Okay, that also shows us here we're going to distribute this -4, so we want to be careful. I'm going to copy the 2x. -4 times -4 is positive 16x, and then I have -4 times 5, which is -20, and that is equal to 7. I'm now going to combine my like terms. So I have 18x minus 20 is equal to 7. I'm going to get the x by itself by adding 20 to each side. And I have 18x is equal to 27. And I'm going to divide each side by 18. Now, at first, this doesn't look like it's going to give us a very nice answer, but actually 27 over 18 reduces to be 3 over 2, or you could say that's 1.5. Either way, we've found x. Okay, so now I'm going to find y. So I can choose either one of those equations to use to find y. Okay, sorry about that. Okay, so we have x is equal to 1.5 or 3 over 2. So now we're going to go ahead and find y. So we can use either of our equations. I feel like the easier equation is the bottom one, so I'm going to choose to use the 4x plus y equals 5. And I'm now going to put in my 3 over 2 or my 1.5 value, either one, for x. 4 times 1.5 is 6, so I get 6 plus y equals 5. Subtract 6 from each side, so I get y is equal to -1. So those are my two answers, but I have to write them together as a final answer. So my final answer is 1.5 comma -1, or if you wanted to write it using fractions, you could say 3/2 comma -1. So that's probably the kind of answer you're going to see in the textbook, is probably the fractional one, but now we need to check that answer in both equations. So we're going to check 3/2 -1 in equation A, and then we're also going to check 3/2 -1 in equation B. So equation A was 2x minus 4y equals 7. And equation B was 4x plus y equals 5. So let's see if this works. Okay, so 2x would be 2 times 3/2 minus 4 times -1 equals 7. Well, the 2's would cancel here, so I would get 3, and then -4 times -1 is plus 4 equals 7. So I get 7 equals 7, and there we go. Let's try the second one. So 4 times 3/2, well, the 4 and the 2 cancel to give 2. 2 times 3 is 6. 6 minus 1 does equal 5. So it works out for both. And therefore, 3/2 comma -1 is our answer. If we wanted to graph those in Desmos, we could plug those equations into Desmos, and we would also get an intersection point at that location. Okay, equation B. We're also going to solve by substitution here. So I'm going to decide what is the easiest variable to get by itself. And right now that looks like probably the y is the easiest one to isolate. So I'm going to, on this bottom equation, add x to each side, and that gives me y equals x plus 3. So I'm now going to take that x plus 3 portion and substitute it in for the y here. So I will have -3x plus 3 sets of x plus 3 is equal to 4. So the important thing here is I have only x. I don't have any y's anymore. One variable is solvable. I'm going to have to distribute that +3. So I copy the -3x, and I have plus 3x plus 9 equals 4. I have to add my terms together. That leaves me with 0x. I'm not going to write 0x. I'm just going to leave it off. So I have 9 is equal to 4, which doesn't make any sense. This is impossible. This is always false, which means there is no solution. So if you think about it, what would have to be the situation to cause two lines to have no solution or to never intersect? So these lines are parallel. They must never meet. Okay, so there's actually no answer. The nice part of that is there's nothing to check. Okay, likewise, I'm just going to go back to this for a second. If you ended up with these x's canceling out and you had a statement like 4 equals 4, which is always true, then there would be infinite solutions because they would be the same line when you graphed them. But on this one, there's no solution. So these lines must have been parallel. Okay, let's take a look at our next example here, which is C. So the nice thing here is that we already have something isolated. So they've done that first step for us. So that's a bonus. Okay, what I'm going to do is take my expression for y and I'm going to substitute it into this y. So I'm going to have 5x minus 2 sets of this entire expression. So 5/2x minus 5, and that is equal to 10. And I'm going to distribute that -2 to both terms. So watch out, we're distributing a negative here. So the 2's will cancel, but I'll get -5x, and -2 times -5 is +10. Now I need to subtract these, and oh, lo and behold, look what I get. What I was just talking about on the last example. This is a statement. There's no more x's involved, but I end up with a statement that's always true. So therefore, these lines are identical when you graph them. Which means the solution is that it's infinite solutions. We couldn't even list them all because everything along those lines is a solution and the lines go on forever. So nothing to check. Let's try D. Okay, well, it looks like we already have a y isolated here. So I'm going to take whatever y is equal to and plug it in for the y here. Of course, what we're noticing about D is that there are a lot of fractions involved. So we're going to have to really put on our thinking caps. Remember, you can always use the fraction button on your calculator as well. Okay, so we have 2/3 y, so that's going to be 2/3 times 1/4 x minus 5/3 is equal to -1. And so I'm going to be distributing this 2/3 to each of those. So I now have, oh, you know what? Yes, this method works. I'm going to show you two ways of doing this, actually. If you do have a fraction button on your calculator, you can stick with this method. Already it's getting a little bit sticky. And looking back at my answer key, I actually have a different way that I showed this one, but I'll show this method first and then show that one. So 2/3 times 1/4 is going to be 1/6. And then 2/3 times -5/3 is -10/9 equals -1. And we could keep going with this. It's just getting a little bit annoying. There's still fractions everywhere. So I'm going to actually, this isn't wrong. We can keep going with it, but I'm going to show you a different way because I'm kind of changing my mind about my strategy here and going, you know what, before we substitute, I want to try and get rid of some fractions. So sometimes that happens. You start going down a path and then you realize, oh man, this isn't looking any nicer as I go through. It wasn't wrong. It's just that maybe there's a better way. So what I'm going to do is get rid of my fractions. So I'm going to choose to modify each of my equations. So I'm going to multiply the top equation by something that will cancel with the 4 and cancel with the 3. In other words, a lowest common multiple of 4 and 3, and that number is 12. So I'm going to give the top equation a makeover. So 12 times y is 12y. 12 divided by 4 is 3, so I have that's equal to 3x. 12 divided by 3 is 4. 4 times 5 is 20. So I can rewrite that equation as 12y equals 3x minus 20. I'm going to do the same thing down here, except I only have to multiply by a 6 this time to cancel with the 2 and the 3. And so I get 3x, 6 divided by 3 is 2. 2 times 2 is 4. So plus 4y equals -6. And now I have a situation where I have no more fractions to work with. So to me, that's definitely got some appeal, right? It's definitely got some appeal. So now I'm going to work with these equations and do a little bit of substitution to solve them. Sorry, just got to pause for a second here. Okay, so there is a little bit of a trick here that we can use to solve this equation. So I just want to make sure, okay, I'm recording properly, sorry. And the little bit of a trick is that instead of isolating x or y, which would cause me to go back into fraction mode on one of these, I'm noticing that the 3x occurs in both. So what I'm going to do is isolate 3x in one of these, and it's a bit of a trick, so I'm going to call it a trick. Isolate 3x instead of just x. And that will allow me to substitute in for 3x. So in my first equation, I could say that 12y plus 20 is equal to 3x. Okay, and now what I can do is I can take that whole 12y plus 20 and put it in place of this entire 3x. So I get 12y plus 20 plus 4y is equal to -6. So the trick was that I didn't isolate it down to a single x. I isolated 3x. So that is another possibility for substitution. So kind of a neat question to look at for that reason. So I end up with 16y plus 20 is equal to -6. I'm going to subtract 20 from each side. So I get 16y is equal to -26. So y is equal to -26 over 16. So not the nicest looking question. and I get that's negative 13 over 8 for my y value. So now I need to find x. I would say most questions that you're going to work with aren't going to be this finicky with the fractions. This one's a little bit annoying, but nonetheless, we can still go on and finish this. So now we're going to go ahead and find x. So I'm going to use my first equation. So y equals 1/4 x minus 5/3, and I'm going to substitute in my negative 13 over 8 over here. And remember, you can use a trick here to get rid of your fractions. So I'm going to multiply everything by 24 because that is the lowest common multiple of 8, 4, and 3. So 24 divided by 8 is 3. 3 times negative 13 is negative 39. 24 divided by 4 is 6. And 24 divided by 3 is 8 times the negative 5 gives me negative 40. So we're getting closer. I'm going to add 40 to each side. So I get 1 is equal to 6x. I'm going to divide each side by 6. So I get 1/6 is equal to x. Okay, so there is my ordered pair. So now I really should be checking that in both of the equations. Just in the interest of time, I'm not going to show that, but now you would check your point of 1/6 comma negative 13/8 in A, and you would also check it in equation B. So the video is getting a little bit long, so I'm going to skip that part, but normally you'd be checking that in both equations as well. Okay, so that takes us to our assignment for 7.4. So as you can see, I chose not to do a textbook version. I chose to do kind of a worksheet version. So I will let you know on the Google Classroom what your assignment is for this section. Thanks for tuning in, and hopefully that helps explain how to solve a system of equations by substitution.